I hope you can hear me. I hope you can hear me at the back, right? Okay. So my talk is going to, so I planned more of a technical talk, but it seems like I just have half an hour, so I will try to provide the main motivation and the key ideas and not go too much into technical depth of these topics. So IR, so I'm a researcher working in information retrieval, that's IR, where I need to find relevant documents for a query. And RAG is more like the application of IR for retrieval augmented generation, because you need to think about question answering systems, where you need to generate an answer. But so it's basically better if you get some context related to that topic, and then you need to use retrievers for that. And then the next step is generation. So that's what RAG stands for, I think. Yeah. So just to give you a brief overview of query performance prediction to start with. So the whole talk is going to be like the importance of performance systems or performance prediction systems for information retrieval and RAG. So for that, we need to start with what is query performance prediction in standard information retrieval. So basically, imagine that you have got multiple queries, but not all queries will give you effective results. Okay, so it's like more like some queries will give you more relevant documents than top ranks, whereas other queries will give you less relevant documents, given that you have fixed retrieval model. So for example, queries like specific queries typically tend to give like better retrieval results, whereas general ones are not that good. So an example is agoraphobia. So with respect to a collection, you tend to think that, okay, there may be a few documents which has got information on that particular topic, which is like, if you are scared of closed spaces, or if you're scared of moving out of your home. So that's agoraphobia, so that's the mental disease, psychological disease. Whereas, so that should be an easy query because there will be like only a handful of documents containing information on that topic, so it should be quite easy to find those information. Whereas for a topic like black bear attacks, maybe there are more documents where, firstly, it has got like more terms in there, so it's a multi-term query, and then the combinations of terms can mean different semantic information needs that you might actually want. So black bear attacks, you are not really sure where exactly, okay? And then like black and bear, these terms can occur in many other documents. So just by, just because these two terms match, you will get documents like that, but they won't be about attacks of black bears. They will be something else. So for this kind of queries, it's usually difficult for retrieval models to get relevant documents in top ranks. But the purpose of query performance prediction models is like to predict a score that given a query and the top rank documents, you just need to find out the score, like how likely is it that I have got relevant documents in the top ranks. So if that score is high, then you believe there is a more belief that the results are good, whereas if the score is low, it tells you that the system doesn't believe that you have got relevant documents towards top ranks. So there are two types of retrieval approaches, or two types of QPP approaches, query performance prediction approaches. The first is the pre-retrieval type, where you don't actually have the top rank documents. Given just the query and the collection, you want to figure out that what's the likelihood that I'm going to get relevant documents with any retrieval model for this particular query. So this is not grounded to a particular ranker or to a particular retrieval model. Whereas the post-retrieval one is like, so the estimates you want to differ from different models. So maybe some models are good at certain queries, the other models are better at some other queries. So you want to capture that nuance of that characteristic, and then you want to come up with different scores. So these models are aware of the ranker itself. So one is ranker agnostic, and the other is ranker aware. Yeah. And this task itself of query performance prediction is not that easy because, okay, so it depends on some factors like the scores of the relevant documents, or the scores of the documents that you retrieve in the top ranks. So one of the insights is that if you have got a skewed distribution of the scores, then probably you have got like more relevant documents in the top ranks, because the scores at the very top are quite different from the scores that are like at ranks 20 or 30. So if that is the case, if it's a very skewed distribution like this, then probably you believe that maybe the results for that particular query are better, because we can draw a line and then separate the very top from the rest, and then probably you believe that these documents are like distinguished from the rest, and they are likely the relevant ones. And that comes from that relevant document clustering hypothesis that if you really have relevant documents, they tend to cluster together, and then probably they will have similar discourse with respect to the query. But this is not always true, because that depends on the ranker as well. So if you take a different ranker, like say for example, Goldberg is a neural ranking model, So the score distributions can be quite different. And then if you just look into score distribution, then it's for the same query, but then there is much more skew in a statistical model than that of a neural model. So score distribution is a valid information or is useful information, but it's not the only one. So it really depends on what ranker you are using, and you have to be careful about these things. So unsupervised approaches, maybe they work well for lexical models, but when it comes to neural models, the score distribution is very different, and then we don't have enough control on how to define the scores because they are learned from parameters, from data. So probably there has to be like other approaches for dealing with this kind of loss. Yeah, so that's not always true. Yeah, this one. So this is when instead of relying on just one information for one particular query, we assume that a query is nothing but one representation of the information need that's associated with something that you want to find. So a particular query from a user is just a sample among many possible expressions of the same information need. So what you then can do is consider all those variants of the query. So say for example, black bear attacks, I could formulate that in a different way. Maybe I can be more specific, like black bear attacks in the US or some particular radius of US, or maybe I can use some other terms as well. So these are all considered to be like query variants. And then what you can do is you can run a standard prediction model on all these different queries, and then can aggregate the beliefs over all of them. So it's not restricted to one particular expression of the information need, but it can iterate for or it can aggregate the beliefs over all different possible information needs. I don't have time to go through all this because these are like standard QPP models, but if you're more interested, we can talk about that offline. So go to the next slide. Yes, as I said, all you need to do is then combine the beliefs from different reference lists, which is obtained from the ranked list of different expressions of information needs, so different queries. Typically, we do some kind of weighted combination, so we have that sigma q and q hat or q dash. So q is the original query, and q dash is usually an automatically generated variant. But then we need to figure out how similar in the semantic space is that variant to the original query, and then you can have some kind of weighted aggregation. Right? So now we know that unsupervised approaches, either you need to work with some heuristics like score distribution, or you need to work by aggregating the information from different variants. But that's something that's coming from heuristics, but maybe we can learn this from data itself. So that's what the supervised query prediction performance models tend to do. So all you need to do is learn a function that maps from a query and the top retrieved documents to a real value score, which you can learn from your data. Okay? Now, the way this works is typically just like learning to rank models would work. But the only difference is that there you have a triple. So you have a query, a relevant document, and a non-relevant document. What you want to do is you want to maximize the similarity of the relevant document with the query and minimize the similarity of the non-relevant document with the query. This also works in a similar kind of way. So what you really have is two queries, okay, not two documents. What you have is two queries, and you know that this query is easier than that query for this particular model, okay, and this query is more difficult than that query. So all you then need to know is a pairwise comparison, which is nothing but a binary variable. So you can just have a sigmoid, a classification head at the top, whereas you can have a pairwise model, which basically encodes the information from the query and the top retrieved documents, but you have got two queries and two sets of documents. Okay, so you encode them. Maybe you can have different kinds of encoders, but this is just a schematic view of encoding them. And then you pass them through a classifier head, okay, which will have trainable parameters that you can learn. If you go to the next slide. So there could be multiple ways of encoding that information. So one of them could be the standard bi-encoder, which is you have two different towers of encoding parameters and one is not dependent on the other. You could even have cross-encoders, which will have more parameters because you just have one encoder model and you fit in everything into that separated by a separated token here, which means that all of them can interact with other ones, right? So you have this whole attention learnable set of parameters that you can learn through this. So this is, cross-encoder is more powerful than the bi-encoder, but obviously it takes more time to train and all that. You can also have something like a late interaction where you work with the individual tokens, but then you have some kind of an aggregation similarity like the max that people typically use in Kohlberg. Even that's possible to encode two queries and the retrieve documents. Okay? Yeah. So now that, let's say we have an estimator, so the next question is, how are we going to use that? Okay, so the main motivation of why do you want to predict the performance of a system is that if you think that the performance is low, then maybe you want to do something else. Maybe then this process is not good enough, and you can estimate that from the data itself. And then maybe for certain sets of queries or certain sets of inputs, you can do some more complex steps. So that will be the whole process or the whole idea of using a QPP in the pipeline or a prediction system in the pipeline, that if the estimator performance is low, then you can fall back to more complex strategies and then try to improve on the results. Okay? If you don't have this feedback mechanism, there will be no way of knowing that if the performance is good or bad. At least here you can try to improve on the performance. Okay? So one of the things, we just go back to the earlier slide. So in this case, what you can do is you can try to reformulate and enrich the query. For IR, if you see that the query performance prediction is low, then what you can do is, we can have some kind of an automated feedback, like take more information from the retrieve documents and then enrich your query, or maybe use a stronger ranker to further improve the results. So this is what it shows, that the performance across queries is not uniform. So if you plot here the per query effectiveness values, in this case we have plotted average precision, but you can work with precision at 10 or NDCG, whatever. So if you have got some information retrieval metric which quantifies how good are the retrieval results, you see that for most of the queries, it doesn't really work well. So here we are trying to plot what happens if if you have a retrieve and re-rank pipeline, or you could have, I don't know, something like a feedback model, just one single retrieval and then followed by a different step, which is a more complex step. That doesn't always work. Okay, so if you just blindly apply some ranking step, it doesn't improve the performance for all queries. On an average, it improves. So if you compute the total area of this part, that's higher. So on an average, that improves your results. And then we tend to believe that, okay, so this is something that you can apply for all queries, but it's not actually true. So if you can figure out that these are the queries for which the performance is low after you apply the ranking step, then it's possible to apply an adaptive technique by which you can do something else for these queries and then improve the results further for the whole set of queries. So that's what we did in this paper. So it's an ECI paper published last year by one of my PhD students who has graduated out. So what she did here was we have a two-stage pipeline of ranking. So you have the initial ranker by PM25, can be a neural ranker as well, like Mono-T5. And then we have the pseudo-relevance feedback, where you take information from the top rank documents and then you enrich your query and then do a second step retrieval. So if given a training set, you can then predict if this is my query, and then for some queries, this ranking or this ranking step works, and then for some queries, it won't work. So all you can then try to do is to learn a map between your topics or the semantic representation of the query terms, and between the decision that whether re-ranking works for those kinds of queries or not. Okay, so given enough training data, you should be able to train a classifier like this. Let's go on. So that was an abstract view of the classifier, but in principle, what you can do is you can have these encodings, and then you have queries and documents, just like we had shown the cross-encoders, bi-encoder stuff. So you can have some kind of encoding of the queries and documents, and then you have a series or a sequence of documents. So you can even have LSTMs connected like this, which is a shortcut for not having too many parameters, or else you can fit everything in a cross-encoder. So this is using bi-encoders and then connecting them in sequence, just to have lesser number of parameters. You can even have a standard cross-encoder. Nowadays, you can have that. In the modern world, you have lots of tokens that are allowed to have, but in that time, the BERT model had only 512 tokens to work with. So we had to do something like this. But the whole idea is okay, so we have got two different sets of given two query pairs. All you're trying to do is to predict a sigmoid, which is the comparison, which query got benefited by applying that re-ranking step. Okay. And one good point, if you just go back to the previous slide, one good point is that if you predict that value from the sigmoid, that acts more like a posterior probability, and in the inference time, you don't even need to use the binary hard decision, whether to apply that step or not. you can even have a soft combination of the weights. So these posteriors are nothing but likelihoods or weights, and then you can then use these weights to combine the two rank lists. Okay? So that's what we did. I'm not going to go to those, but just change the slide. So it shows that while we had used those weights to combine the two different rank lists, the initial one and the one with feedback, we show that firstly we can predict the accuracy by 80%, so that's like a decent enough performance. And the second is that if I apply that step adaptively, not for all the queries, if I use that classifier's decision and then use the posteriors to have a weighted combination, that outperforms the case where we have like applied that step for every query. Okay? So this would be somewhere like PRF, that's 0.4321. That's when we do the PRF step for every query. Whereas if I do that selectively, then I can get much better results. Okay? So that's what the work. I'm not going through all the results, but the whole idea is there. If you're more interested, then you can read that paper. Next slide. Okay. So now, we have seen that how QPP approaches can be useful in information retrieval pipelines. But nowadays, we are working with generative models, and it's more like a question answering now, where we're generating the answer directly. So probably we don't need retrieval. That's what your first think might be. That probably, we don't need rankers anymore. But that's far from being true. There are two basic reasons why you want to still use a ranker. The first is that LLMs can hallucinate. Okay, all the generative models, they can cook up something. That's not true. So one of the ways is like to ground that generation to a collection of documents to act as references. So that will increase your trustworthiness that, if that's my answer, then I can refer back to these actual documents in a collection to support the answer generated. Okay, so that's one of the use cases for this. The other use case is for retrieval augmented generation. So if you just get to the next slide. The other use case is for retrieval augmented generation, where the whole idea is like you retrieve semantically similar content and then put that as a context to the generator so that it generates better answers. So an example for that is, so this is taken from an actual data set, the NQ data set. So where the question is, who is Aziz Hashim? So if you do not have any context, if you just generate a zero-shot answer, it says that Aziz Hashim is a renowned American chef, restaurateur, and food writer of Indian descent. Okay, but that's not true. What he is actually is that he's an entrepreneur. And the whole fact that during his graduate days, he worked at a restaurant. And the LLMs are pretty good at connecting these things, right? So it has picked up the information, and it now thinks that he is a renowned chef, but he's actually not. He's a renowned entrepreneur. So LLMs can make mistakes like this, but if you can find out documents and then which is about Aziz Hashim and then say that he's a leading expert on franchising and highly regarded executive in the US and stuff like that. So if you provide some context to the document, then the generated answer is not incorrect. It's the correct answer then. So it's usually for this reason that you still want to have topically relevant documents to be brought in and then fed as context to the generated answer, or before you generate the answer, so that you get better quality answers. So that's what we usually do. And then QPP can play a role, because in that case you can then kind of predict that are the documents that we are retrieving, are they good enough to get correct answers? So this is one of the work that my student did this year, and he won the Best Paper Award in ECIR, was that he was trying to predict the context size that you need for every query. So not every query you would need the same amount of context. So for some queries, you don't need any context at all. Okay? For some queries, you need a small number of context documents. For some other queries that are more complex in nature, maybe you need more documents. So what we then did was we tried to predict that context size for a query. Just like we predicted which query should be benefited by application of a re-ranker step, here we are trying to predict the context size. So again, it's a classifier that given a query, will map it to a class, which can be a 0, 1, 2, up to some max number of context size that you may want. Okay? So given a training set, and there you know the ground truth answers. So there you know that compare the zero-shot generated answer with different values of context sizes, and you know that which one is the best. And then that acts as a ground truth for your training set. And then once you then learn this classifier, in the inference time, all you need to do is to invoke that classifier, and that will predict that, okay, for this you need 1 context size, for that you need 5 context size, and so on, right? So that's what we typically do, and then go to the next slide. So the results are quite convincing because it shows that if you just have a fixed context size, the results are not that high, but with an adaptive context size, the results can be quite higher. We have seen improvements like over 10% to 15%, I think. So it really shows promise, this method, that you can adaptively decide the context on the basis of the data itself. Okay. How much time do I have?
Let's see, about 10 minutes.
10 minutes. I'll try to go. So, so that was one of the ways in which you can adaptively control the pipeline, which is like variable context sizes for different types of questions. Now, what this idea tries to do is like you can have adaptive RAG workflows as well. So in this case, so this basically is a foundational work that tries to improve on the ranking step itself. So the ranking, as we know, is often like it tries to find relevant documents for queries. So that's more like a semantic match or relevance-based matching that we want to do. In this case, in this study, we wanted to see like whether relevance is correlated with the downstream performance of RAG at all. So sometimes maybe relevant documents, not only, it's not just relevance that influences the quality of the generated answers. Maybe it's something else. That's what we wanted to validate, that whether there is something other than relevance that can affect the final answer quality. So yeah. So we call that utility. So maybe utility is, relevance is related to utility, obviously. But maybe there are some other things as well, which we wanted to investigate. So here we show that there is a small positive correlation between relevance and utility. So utility is like the downstream performance gains that you'll get by using that context, versus if you don't use it. So the utility is not always highly correlated with relevance. So there are something else, maybe non-relevant documents, but something related to semantics of those non-relevant documents that could still help to improve the performance of RAG systems. So these correlations are small, but there is a small correlation. As you can see through the scatter plots here, and so on. So this idea tries to exploit adaptive RAG systems where there are 2 steps here. One is retriever and one is the generator. So you can try to predict whether contexts are useful for the downstream performance and whether the generated answer is good enough or not, right? So there are 2 different kinds of predictions that you can do. One at the retriever end and one at the generator end. So we call that RPP, retriever performance prediction, and generative performance prediction, GPP. So we have seen, so my student has found out that there are several factors. As I said, relevance is not the only one. There are other factors as well. So the factors will be entailment, like it's somewhat related to coherence in the text, but also relates to reading effort of the elements, right? So it's like how smoothly does this sentence follow from the previous sentence, okay? So it's like how coherent or how well connected the sentences are. If it's like more coherent, then he has saying that there is a positive correlation between the performance of those documents, the context, in the question answering process. Posterior is like how confident are the LLMs. So if you use a document for conditional generation, maybe that leads to decreased confidences. So that's probably not good. You want documents for which the LLMs can predict with more confidence. And positional bias as well. So as you might be knowing that things get lost in the middle. So if you have got relevant stuff at the front and at the back of a context, so that's the most back one. So this ones will be fed to the decoder first, and then these ones. So the attention spans usually work well at the beginning or at the end. Okay, things are not that common or things are not that smooth in the middle, because that's how these models are kind of pre-trained in all these encoder models, that we put more important stuff at the beginning of a document and at the end of a document. Things are not that relevant in the middle. So somehow these pre-training models have captured those things, and the attention weights are like less. There are not much of weight in the middle part of an attention span. So we need to be making sure that there are not too many relevant documents in the middle, whereas we try to pack in as much relevant stuff at the end and at the start of a context. Next one. Yeah, so then we try to apply the generated answers, the retrieval performance prediction and the generated performance prediction into an adaptive RAG workflow. The next one. Yeah, I don't think that's just go back, I'll just talk through it briefly. Yeah. So basically we'll have like two different predictors, and maybe there is something that you can do with like how the predictors will interact with themselves, because it's not completely independent. The retrieval performance prediction will depend somehow on the generative performance prediction and so on. So we already have seen that the retrieval performance prediction, you can try to have like larger context sizes, or you can try to have a more downstream specific ranking model to be able to retrieve better documents. And the same goes for generative performance prediction as well, because you can then have like, maybe you can have a more complex flow of generating the answers. We'll look at one particular example, so we won't be having time to cover all that, but one particular example of how this can be applied. So we did, one of the things that we wanted to do was like, if you have got different rankers, then maybe you can choose like which ranker is the best one for a particular query, okay? So usually QPP, you predict the performance of a query, or for multiple queries, but keeping the ranker fixed, you want to choose like which query is the best or which query is better. Here we want to fix that query and choose which ranker is the best, okay? Go to the next slide. That's the standard QPP, where you have got fix one query or fix one ranker and got multiple queries and then predict the best one. That's standard QPP workflow. The next one is where we've got multiple rankers, so it's more fine-grained performance evaluation that we want to make. Fix the query, then we want to predict like which ranker is the best. And you can also do a global kind of correlation that among a given set of queries and among the different set of rankers, how do you want to route each of the queries to independent rankers so that you get the best results. So I'm not going to go through the results. So this is what you can do in principle. You can apply QPP on multiple rankers, and then you can get the best. You can have a ranking of those ranking models in some sense, and you can measure correlations like this. This one. Yeah. So then all we want to do is, from these kind of predictions, we want to go to predicting. Yeah, so we want to have like QPP till now, it was more like predicting the performance or retrieval performance. But here, if you want to apply that to a RAG, we want to see like how good they are downstream. Okay, so there will be some downstream performance evaluation that you can do. Next one. So in this case, so it's a very simple idea. What we did was like, we computed the QPP scores, and then we had a weighted fusion of the different QPP models. So if you can have a baseline fusion where you just have a reciprocal rank fusion or a combination of the scores, so they are the baselines, which is more like, you are not doing a per query based combination. But here, what you can do is like, based on the QPP weights, you can have a QPP weighted combination of those different rankers, and you can get much better results. And all the green values are where this adaptive combination gives you better results. Next one, I think I'll stop somewhere here, one or two slides from here. So this one was a different idea where it's not only just trying to use different sources for the retriever, like different rankers that we looked at, it also tries to combine like different sources. So an example is like if you have a fact verification task like this, so maybe for some cases, you will be finding more useful stuff in labeled collections, whereas in some other cases, maybe there will be like unlabeled data, like Wikipedia or other different sources from which you may get better information. Okay, so it really depends on the type. So it may be worthwhile to choose which collections to use for different types of queries, with different kinds of weights, and combine that information. Okay. Go to the next one. And what we do here is like, the idea is very simple. Just like we have different rankers, we have different rankers here as well, a sparse, bioencoder, all these different types of neural rankings. But we have like different collections here. Okay. So we have got two dimensions here. One is the source, and the other is the different rankers that we're using. So we need to do some kind of combination. So the first step here is the reciprocal rank fusion that we can do and combine rank list of combined documents from all these lists. And the second one is like we have got two different sources. So we have like two different distributions of the similarity scores. And then we can combine them into a single rank list. So it's like a hierarchical combination in the sense that you're combining rankers in the first step, and then you're combining information from different sources in the second step, and putting them as context to an LLM. Okay? One more slide, I'll stop. So if you just, we did that. So zero shot is not that good, and then standard, if you do it from a standard collection like the labeled data itself, like context learning, you get improvements over this, but it's not that high. Whereas if you do it only from the unlabeled source, you get similar performance. But if you then combine things from two different sources and multiple different rankers in that adaptive way, you can improve your results by about 10%. Okay? So that's like really, again, a promising set of results that we have seen. And as it turns out that it can vary across different tasks. Like fever is a standard benchmark on which you see that the labeled and unlabeled contribution is different from SciFact. So SciFact, it tends to put more importance on the unlabeled data than the labeled one, because the labeled one is too small. So you have to find more information that you can find from external information. Okay, so it's a way of adaptively controlling like what information you want to get from what sources and using what rankers. I'll stop here. I won't take much of your time. So if you have any questions, then please let me know.